Have you ever looked at an airplane propeller and simply thought, well, that's just a big fan spinning around, pushing air? It seems pretty straightforward, right? But okay, let's unpack this. Because beneath that deceptively simple appearance lies, well, a breathtaking symphony of engineering, complex physics, and meticulous design. All of it working to keep aircraft safely and efficiently in the sky. Today, we're taking a deep dive into an essential yet often overlooked component of flight, the aircraft propeller. It is truly so much more than just spinning blades. We've been digging through a comprehensive aviation maintenance manual, and let me tell you, it reveals layers of hidden genius, stuff you never even knew existed for this one piece of equipment.
And that's precisely our mission with this deep dive, to peel back those layers, move beyond just a superficial understanding. We really want to help you grasp the why behind every aspect of propeller design, its fundamental function, and the rigorous maintenance that's absolutely critical. I mean, consider the sheer genius of early pioneers like the Wright brothers. They didn't just bolt a fan onto their aircraft. They had this profound realization about propellers. They saw them as sophisticated rotating airfoils, not just simple pushers of air.
Rotating airfoils,
Yeah.
like wings, but spinning.
Exactly. And Orville Wright himself, thinking about how hard propeller design was, famously said, and I think this just perfectly captures the incredibly interconnected nature of it all, on further consideration, it is hard to find even a point from which to make a start, for nothing about a propeller or the medium in which it acts stands still for a moment.
Wow. So everything affects everything else.
Precisely. He truly understood that if any one variable changes, it affects all the rest, because they are so fundamentally interdependent. So this deep dive will hopefully reveal those hidden forces, the clever mechanisms, and the meticulous care required to keep these crucial components flying safely and efficiently, constantly pushing us forward.
All right, so let's start at the very beginning. How does a propeller actually generate thrust? When you look at an aircraft wing, you see its curved shape, right? Designed to generate lift. Well, if you could take a cross-section of a propeller blade, you'd see it's essentially an airfoil, very similar to that wing.
Yeah, the basic principle is the same, aerodynamics.
Right. The key difference is, instead of generating lift upwards, it's generating thrust forwards. So the curved side of the blade, the bit that creates that aerodynamic action, is called the blade back, or cambered side.
Just like the upper surface of a wing.
Exactly. And the relatively flat side, the one that's kind of doing the pushing against the air, that's the blade face.
Like the wing's undersurface.
Yep. Now, here's a fascinating detail you might not expect. Propeller blades aren't simply flat. They're actually twisted from root to tip.
That twist is crucial.
It might seem counterintuitive, but it's a brilliant bit of engineering. It compensates for a simple fact. Different parts of the blade move at vastly different speeds as the propeller rotates. Think about a point right at the hub versus the very tip.
The tip is moving much, much faster.
Significantly faster. For example, at, say, 2,200 RPM, the tip might be zipping along at over 750 kilometers per hour, while a point just a foot from the hub is only doing about 250 kph. Huge difference. So for optimal efficiency, every part of the blade needs to interact with the air just right.
It needs the right angle for its speed.
Precisely. So near the hub, where the blade is moving slower, you'll find a higher pitch or angle. It's designed to bite into more air. As you move towards the tip, where the blade is moving much faster, the pitch gradually becomes shallower. This progressive twist ensures that every part of the blade generates thrust efficiently across its entire span.
That twist is absolutely critical, yeah. And it brings us to a crucial distinction that pilots and engineers grapple with: the difference between blade angle and angle of attack, or AOA.
Okay, two different angles. How do they relate?
Well, the blade angle is the fixed relationship between the blade's chord line. Think of it as a line from the leading edge to the trailing edge and the propeller's plane of rotation. For a basic fixed-pitch propeller, that angle is set once and for all during manufacturing. Can't change it.
Set in stone, basically.
Pretty much. For more advanced controllable pitch propellers, it's the angle you physically set the blade to, or the system sets it to. But the angle of attack, that crucial aerodynamic concept, is dynamic. It's the angle between the blade's chord line and the relative airflow it encounters.
The airflow relative to the moving blade.
Exactly. And that angle constantly varies with the aircraft's forward speed. So at low airspeed, like during takeoff, you'll have a high angle of attack for a given blade angle. At higher speed, cruise maybe, you'll have a low angle of attack for that same blade angle.
Right, because the incoming air direction changes relative to the blade.
You got it. And what's truly fascinating is how constant speed propellers cleverly manage this. They automatically adjust the blade angle in flight, changing that fixed angle to maintain a small, highly efficient angle of attack.
So they're chasing that sweet spot.
Constantly. Typically, it's between 2 and 4 degrees positive AOA. They adjust the blade angle to keep it right there across a wide range of flight conditions. This is how they maximize efficiency, whether you're taking off, climbing, or cruising.
Okay, that makes sense. It's optimizing the bite of the air constantly. And speaking of efficiency, that leads us to the primary forces acting on a propeller. And here's where it gets really interesting, because these aren't just gentle breezes we're talking about. These are intense, powerful forces that the propeller has to constantly battle and engineers have to design for.
Oh yeah, the stresses are enormous.
The first one, and arguably the most dominant, is centrifugal force. This is the force that relentlessly tries to pull the rotating blades right out of the hub.
Just wants to fling them outwards.
Exactly. And we're talking about forces that can be measured in tons at high RPMs.
Yeah, absolutely. Tons. It's incredible the forces involved.
Imagine that immense outward pull. The sheer magnitude of this force is why the integrity of the blade material and the strength of the hub connection are absolutely paramount. A tiny defect near the root or in the hub itself could lead to, well, a catastrophic blade separation.
It's the #1 design consideration in many ways.
Then we have torque bending force. This is essentially the air resistance acting on the blades. It tries to bend them opposite to their direction of rotation.
Like drag, basically.
Kinda, yeah. It's the drag created as the blades slice through the air, and it's a constant load the propeller structure must withstand. Pilots actually have to compensate for the aircraft's reaction to this torque.
Right, the whole plane wants to roll the other way.
Next, there's thrust bending force. As the propeller generates the forward thrust that pulls the aircraft, this force tries to bend the blades forward. It's particularly prominent at the thinner blade tips, where the section is more flexible. You can actually sometimes see them flex slightly under load.
Especially on older, maybe larger props.
Now, for two forces that constantly fight each other in a delicate balance. First, aerodynamic twisting force, or APF, sometimes called ATM for aerodynamic twisting moment. This force tends to rotate the propeller blades towards a high blade angle, a higher pitch.
Okay, why does it do that?
It's generated because the center of pressure on the blade, where the aerodynamic forces are effectively concentrated, is actually slightly forward, nearer the leading edge of the blade profile. This offset creates a twisting motion that tries to increase the blade's pitch.
Ah, so the lift isn't perfectly centered, creating a lever effect.
Exactly. And finally, counteracting that is centrifugal twisting force, or CTF, also called CTM for centrifugal twisting moment. This one is typically more powerful than ATF. As the propeller rotates, the mass of the blade on each side of its rotational axis naturally tries to move towards that axis, which in turn acts to reduce the pitch, move it towards a low angle. Think of it like a figure skater pulling their arms in to spin faster. The mass wants to be closer to the center of rotation.
Right, and that action pulls the blade towards a lower pitch, and the higher the RPM, the greater the CTF effect becomes.
So these two twisting forces, ATF wanting high pitch, CTF wanting low pitch, are always there.
Always battling it out. And this is where the clever engineering truly shines. These inherent forces aren't just something engineers have to overcome. They are actively harnessed in controllable pitch propellers.
They use the forces themselves.
Absolutely. For instance, the powerful centrifugal twisting moment, CTM, which naturally wants to move the blades to a low pitch, is often used as the primary force for that movement in many designs. Conversely, the aerodynamic twisting moment, ATM, which tries to increase pitch, can be incorporated maybe with counterweights or springs to assist in moving the blades to a high pitch or feather position. So these aerodynamic and centrifugal tendencies become active, working components within the propeller's pitch control system, allowing for remarkably precise adjustment in flight.
That's brilliant. Turning physics against itself, almost.
Yeah.
It's truly remarkable how engineers turn these fundamental forces of nature into sophisticated control mechanisms. But beyond the forces acting on the blades themselves, there are also larger aerodynamic effects that impact the entire aircraft. And pilots have to be acutely aware of them, right?
Oh, definitely. These are things you compensate for constantly, sometimes without even thinking about it after a while.
First up, you might have heard pilots talk about P factor, or asymmetrical thrust.
Yep, especially noticeable in climbs.
Exactly. When the nose of the aircraft is raised, the descending propeller blade, the one moving downwards, actually has a greater effective angle of attack than the ascending blade moving upwards. For propellers that rotate clockwise when viewed from the cockpit, which is most common on single-engine planes, this uneven thrust creates a subtle but persistent left yawing moment.
Makes the nose want to swing left.
Right. So pilots flying these aircraft are constantly applying a little bit of right rudder to keep the plane flying straight, especially during takeoff and climb. It's not an engine problem. It's just an aerodynamic reality of the propeller operating at certain attitudes.
A fundamental effect.
Then there's torque. This is a direct application of Newton's third law for every action. There's an equal and opposite reaction. As the propeller revolves powerfully in one direction, the engine, and by extension the airplane itself, tries to rotate or roll in the opposite direction.
The more power, the stronger the roll tendency.
Yep. Greater power, greater RPM, greater torque effect. You see extreme examples of this in aerobatics, where pilots can perform torque rolls by deliberately using this rotational force to spin the aircraft.
Using it to their advantage.
Another significant effect is the slipstream effect. The air spiraling off the propeller doesn't just go straight back. It creates this kind of corkscrew motion that washes over the fuselage and the tail surfaces.
It wraps around the plane.
And this spiraling slipstream can hit the vertical stabilizer, the tail fin, at an angle. This creates yet another yawing force, making the nose want to yaw left again, usually. It's particularly noticeable during takeoff, especially in older tailwheel aircraft with their geometry. So it's another subtle force the pilot has to constantly manage with rudder input.
Adds to the P-factor effect, often.
And finally, we have to talk about vibration and resonance. Propellers are subjected to constant mechanical and aerodynamic vibrations. That's just part of spinning something that fast. But if these vibrations become excessive, they can cause high levels of blade flexing. And that flexing can actually work harden the metal over time.
Which makes it brittle.
Exactly, making it brittle and eventually leading to catastrophic failure. This is why you'll often see red arcs on an aircraft's tachometer, the RPM gauge. These red arcs indicate critical RPM ranges that pilots must avoid for continuous operation.
Don't hang out in the red zone.
Right. It's okay to accelerate or decelerate through them quickly, but you don't want to linger in that range. These are RPMs where the propeller might hit a resonant frequency, causing dangerous levels of flexing and potential damage. They even talk about nodal points where this flexing concentrates.
It truly highlights how every part of the propeller system is under immense dynamic stress. It demands precision in both design and construction, which brings us nicely to how these incredible components are actually built. We can see a fascinating evolution in materials and craftsmanship over the years.
Yeah, let's get into the construction. Let's start with the historical, yet still surprisingly relevant, fixed-pitch wooden propellers. While many are found on older or vintage aircraft, you still find them on some smaller, simpler planes today. In the early days, pioneers meticulously crafted these from laminated wooden blanks. They weren't solid blocks of wood.
No, that would warp and crack too easily.
Right. They were built from multiple layers, maybe 5 to 9 layers, of carefully selected, well-seasoned hardwoods like birch, mahogany, cherry, black walnut, even oak, glued together with strong, waterproof resin. This layering, often with alternating growth ring directions, helps minimize warping and cracking over time.
A bit like plywood construction, but much more precise.
The major advantage of these wooden props is that they're relatively lightweight, rigid, economical, simple, and comparatively easy to replace if damaged. However, their big disadvantage, as we mentioned, is that you cannot change the blade pitch after manufacture. It's fixed.
One speed, one condition is optimal.
Exactly. This limits their efficiency to a single optimal condition. So you might have a climb prop, lower pitch, shorter diameter maybe, for max power and RPM on takeoff, or a cruise prop, higher pitch, maybe longer diameter, for better fuel efficiency at cruise altitude. You essentially have to pick your priority when you buy it.
A compromise, always.
To protect the leading edges from erosion, especially near the tips where speeds are highest, wooden propellers are often fitted with metal tipping, usually brass, monel, or stainless steel, secured by screws and rivets. Crucially, these metal tips have small drain holes near the very end. These must be kept open to prevent moisture from rain or condensation building up inside the tips, which could cause imbalance or rot.
Little details, big consequences if ignored.
And proper storage is also key for wood props. They should ideally be stored horizontally to maintain even moisture content and prevent warping. Keeping them out of extreme heat or direct sun is important too. They mount to the engine via forged steel hubs, which can be splined, tapered, or use bolted flanges. Proper torquing of the mounting bolts is critical, usually in a star pattern, small increments, rechecking after initial flights, even checking with seasonal humidity changes. Safety first. Magneto's OFF aircraft chalked before touching the prop.
Absolutely. From the craftsmanship of wood, we eventually transitioned to more durable materials, of course. Metal fixed-pitch propellers became common, especially on light aircraft. These are often made from a single piece of forged, anodized aluminum alloy. Duralumin was an older name for a common alloy.
What were the advantages over wood?
Well, arguably lower maintenance, less susceptible to moisture damage. They offered better cooling near the hub because the metal conducts heat away. And importantly, specialized repair stations could actually twist the pitch slightly within limits, offering a form of ground adjustment not possible with wood.
So, a bit more flexibility even if fixed pitch.
A little bit. Now, while the source material sometimes implies they're lighter because they don't need heavy clamping hardware like some wood props, generally, an overall metal propeller is actually heavier than its wooden equivalent. That's a key trade-off. These metal props are identified by precise stampings on the hub. Serial number, model number, type certificate details, production certificate, even how many times it's been reconditioned. The model number itself often tells you a lot. Like Macaulay's 1B90CM tells you blade design, diameter, and engine compatibility.
Lots of info packed in there.
For larger, often older aircraft, particularly from the WWII transport era, you'd find steel propeller blades. These are usually hollow to save weight, but despite that, they still possess a noticeable heft. Very strong, but heavy. Today, though, the cutting edge is really composite propellers. These modern blades are increasingly common and are quite sophisticated pieces of engineering.
What are they made of?
They're typically constructed with numerous layers of carbon fiber laminates, sometimes fiberglass or aramid fibers too, often wound around a lightweight core, maybe a polyurethane foam. They usually have a metal blade shank for strength at the hub connection. They'll include an erosion strip, often tough nickel, bonded to the leading edge to protect against damage, and sometimes internal lightning conductors for safety.
And the advantages?
The big ones are that they are significantly lighter than metal props, often stronger, and can be shaped into more complex, aerodynamically efficient profiles. This means better performance and potentially better fuel economy.
So, lighter, stronger, more efficient. Sounds like a win-win-win. Okay, so we've talked about the materials, wood, metal, composites, and how they're built. But how are these blades actually structured and categorized by their function? Let's quickly break down the blade elements. The blade station is simply a specific measurement point along the blade's length, measured out from the center of the hub, like mile markers on a highway.
Used for reference during design and maintenance?
Right. Then you have the blade face, which we said is the relatively flat, high-pressure, thrust-producing side facing the pilot. And the blade back, the curved, low-pressure, cambered side facing away. The hub is the central assembly that attaches the propeller to the engine crankshaft. The blade butt, or blade root, is the thickest part of the blade, the portion that's actually inserted and clamped into the hub. And the blade shank is the transitional area connecting the root to the main airfoil section of the blade.
Kind of the neck of the blade.
Exactly. Remember that twist we talked about earlier? The pitch, angle, and chord width, the distance from leading to trailing edge of the blade, change along its length. This accommodates those differing airspeeds. The tip moves much faster than the root, so the blade angle needs to gradually decrease from root to tip for optimal performance across the whole span.
Tailoring the shape to the speed at every point.
Now, moving on to the types of propellers based on pitch control. This is where you see the real evolution of propeller technology, in that relentless pursuit of greater efficiency in flight. The simplest, as we discussed, is the fixed-pitch propeller, designed for a single optimal speed and condition, like takeoff or cruise. Simple, inexpensive, common on lower power aircraft. The pilot has zero control over its pitch in flight.
What you see is what you get.
Pretty much. A slight step up was the ground-adjustable propeller. With this type, the pitch can be changed, but only when the propeller isn't turning, usually by loosening clamping mechanisms at the root. You'd set it on the ground for a specific mission, say a climb setting for operating from a short, high-altitude field, but then it acts just like a fixed-pitch prop for the rest of the flight. Not very common these days.
A bit fiddly and still a compromise once airborne.
Next, the controllable pitch propeller. This is a big leap. It allows the pilot to actually change the blade pitch in flight for better performance in various conditions. It could be a simple two-position system, maybe low pitch for takeoff, high pitch for cruise, or fully adjustable through a range. This allowed pilots to start adapting the propeller's performance to different phases of flight.
Getting closer to optimal performance across the board.
But the real game changer, the one most common in higher performance general aviation and larger aircraft, was the constant speed propeller. This is the next evolution. It automatically adjusts pitch using a sophisticated device called a governor to maintain a constant engine RPM that the pilot selects. It does this regardless of changes in aircraft load or attitude, like climbing or diving.
So the engine stays at its happy speed.
Exactly. This ensures the engine is always operating in its most efficient RPM range, maximizing power when needed, or maximizing fuel economy during cruise. It's incredibly clever.
A huge jump in efficiency and performance.
Now, for multi-engine aircraft, a crucial safety feature is the feathering propeller. When an engine fails on a twin, you absolutely don't want that dead engine's propeller windmilling in the airflow. It creates massive drag and can potentially cause further damage to the engine.
Like a giant air brake on one side. Very bad.
Very bad. Feathering propellers can rotate their blades to an angle of approximately 90 degrees, so the thin leading edge is pointing directly into the wind, parallel to the flight path. This minimizes drag from the inoperative engine, vastly improving the aircraft's glide performance and handling, and preventing further damage from windmilling. These propellers typically use oil pressure to move the blades to a low pitch, but then other forces like blade flyweights, springs, maybe compressed air, drive the blades to the feathered, very high-pitch position when oil pressure is removed.
A critical safety system for twins.
Beyond just feathering, some propellers, primarily found on turboprops, are also reverse-pitch propellers. These can change their blade angle to a negative pitch, meaning they actually push air forward instead of backward.
Creating reverse thrust.
Exactly. This is incredibly useful for aerodynamic braking after landing, significantly shortening rollout distances, and reducing wear and tear on the wheel brakes. It can also sometimes be used for backing the aircraft up on the ground or for seaplanes maneuvering precisely on the water. The full range of pitch for some of these high-performance turboprop propellers can extend all the way from full reverse through zero thrust, flight range, feather, and sometimes even beyond.
A very wide operational range.
Finally, we should briefly mention propeller location. The most common configuration by far is the tractor propeller, mounted in front of the engine structure, pulling the aircraft through the air. They generally experience lower stresses because they operate in relatively undisturbed, clean air ahead of the wings and fuselage.
Standard setup for most planes.
Less common, though you see them on some experimental designs, amphibians, or historical aircraft, are pusher propellers. These are mounted behind the engine structure, pushing the aircraft. While they might offer some aerodynamic advantages like cleaner airflow over the wing, they can be more complex structurally and operate in more turbulent air coming off the airframe.
Different set of trade-offs.
And on twin-engine aircraft, you might encounter counter-rotating propellers. This means the propellers on each engine rotate in opposite directions, one clockwise, one counterclockwise. This has the significant aerodynamic benefit of canceling out those torque and P-factor effects, making the aircraft easier to handle, especially if an engine fails. It eliminates the concept of a critical engine, the engine whose failure would most adversely affect control.
A smart design feature for twins. All of these configurations, regardless of type or location, require incredibly precise installation and maintenance. When it comes to propeller removal and installation, caution is absolutely paramount. You always follow the manufacturer's specific detailed procedures. This includes using the correct tools, applying the right torque values, and paying close attention to any indexing marks for reinstallation. Getting the prop back on in the exact same orientation relative to the crankshaft is often critical for maintaining dynamic balance and preventing potentially damaging vibration. And of course, propeller clearances, ensuring enough space between the spinning propeller tips and the ground or water for seaplanes and nearby aircraft structures like the fuselage or landing gear, are meticulously defined in regulations to ensure safety during operation. Can't have those tips hitting anything.
No, definitely not. That pursuit of greater control and efficiency is just relentless in aviation, isn't it? And it's not just about shaping the blade perfectly. It's about managing those incredible forces we talked about, centrifugal, bending, twisting, turning them from potential problems into controllable elements. This leads us perfectly into the true brains of the more advanced propeller systems. Exactly how pitch is controlled in flight.
Right, moving beyond just fixed blades.
As engine power and aircraft capability increased over the decades, the need for more dynamic pitch control became really evident. Fixed or ground adjustable props just couldn't cut it for higher performance. So we moved to systems where the pilot, or eventually the system automatically, could change pitch in flight. Understanding the relationship between propeller pitch, RPM, and manifold absolute pressure, MAP, is key here for piston engines.
They're all interconnected.
Think of it this way. If you increase the blade angle, the pitch, it takes a bigger bite of the air. This increases the angle of attack and the load on the engine. This makes the engine work harder, right? So it tends to slow down the RPM unless you give it more horsepower via the throttle. Now, interestingly, at a constant throttle setting, if the RPM slows down because of the increased load, the manifold absolute pressure, MAP, which measures the pressure in the intake manifold, will actually increase.
Because the engine isn't sucking as hard at the lower RPM.
Exactly. Less air is being pulled into the cylinders per unit of time. Conversely, if you decrease the blade angle, lower pitch, the load on the engine lessens, the RPM speeds up. And because the engine is now pulling more air in faster, the MAP decreases. So by changing the blade angle, you effectively control the load on the engine, which in turn allows you to control the engine's RPM independent of the throttle setting to some extent.
The prop control manages RPM. The throttle manages power, or MAP.
Precisely. This is beautifully illustrated in how a constant speed propeller operates in different phases of flight. During takeoff, when you need maximum power and thrust, the pilot sets the prop control for high RPM. The governor automatically sets the propeller blades to a low pitch. This low blade angle keeps the angle of attack small and efficient at low airspeed, allowing the engine to spin up to its maximum rated RPM for maximum power and thrust.
Gets you off the ground quickly.
As the aircraft gains speed and transitions into a climb, the relative airflow changes. To maintain that high RPM set by the pilot, the governor automatically senses the tendency for RPM to increase and commands the propeller to change to a higher blade angle, or pitch. This higher pitch takes a bigger bite of air, increasing the load, and keeps the RPM constant, while still maintaining that efficient angle of attack as the airspeed increases.
Adapting to the changing conditions.
Then, in cruise flight, less power is generally required for level flight. The pilot typically reduces power by lowering the MAP with the throttle and also selects a lower RPM with the propeller control for better fuel economy and reduced engine wear. The governor responds by setting an even higher pitch, coarser blade angle, to maintain that lower target RPM at cruise airspeed. It's constantly adapting, like a really smart automatic transmission in a car, always keeping the engine in its optimal operating range for the selected phase of flight.
It's a beautiful system. And at the heart of that constant speed system, the component doing all the sensing and commanding is the propeller governor. Think of it as an engine RPM sensing device that also incorporates its own high-pressure oil pump. Its primary job is to respond instantly to any change in engine RPM, deviating from the RPM set by the pilot.
How does it do that?
It does this by directing engine oil, which it boosts to a higher pressure, either to or from the propeller's hydraulic actuating cylinder or piston. This change in oil volume inside the propeller hub then precisely alters the blade angle. The pilot's propeller control lever in the cockpit doesn't directly move the blades. It simply adjusts the tension on the governor's internal speeder spring. This spring tension sets the target RPM the governor tries to maintain.
So the lever tells the governor the target, and the governor figures out the pitch.
Exactly. It's a constant balancing act. Inside the governor, there are rotating flyweights. Centrifugal force tries to throw these flyweights outward as the engine spins. The speeder spring pushes against them, trying to keep them inward. When the forces are balanced, the engine is on speed. If the engine speeds up or slows down, the flyweights move, pushing or pulling a pilot valve, which then directs the high-pressure oil to make the necessary pitch correction.
It's a feedback loop.
A very precise hydraulic and mechanical feedback loop. It's constantly managing that dance between several fundamental forces we talked about earlier that influence blade angle. You've got the centrifugal twisting moment, CTM, always trying to move blades to low pitch. You have the powerful propeller governor oil pressure, which in most light aircraft single-acting systems is directed to move blades to low pitch as well. And opposing these, you have forces trying to move the blades towards high pitch. Propeller blade counterweights, often built into the blade root, internal springs, sometimes pneumatic pressure, air charge, and that smaller aerodynamic twisting moment, ATM.
So oil pressure and CTM push low, counterweights and springs push high.
Generally speaking, for many common systems, yes. The governor oil pressure is the critical controlling force because it's the most powerful. It can overcome the counterweights and springs to drive the pitch lower when needed. When oil pressure is reduced or removed, the counterweights and springs take over and drive the pitch higher. The governor constantly tries to maintain that on-speed condition.
Can you walk us through the different conditions? On-speed, underspeed, overspeed.
Sure. On-speed condition. This is the ideal state. The engine is running exactly at the RPM the pilot selected via the prop lever. The centrifugal force on the spinning flyweights inside the governor perfectly balances the tension from the speeder spring. The pilot valve is centered, meaning no oil flows to or from the propeller's hydraulic cylinder. The blade pitch remains constant. This is the desired state.
Everything's balanced.
Under speed condition. Now imagine the engine RPM drops below the pilot's set target. Perhaps you pull the nose up into a steep climb without adding power. The flyweights sense this reduced RPM. They move inward because there's less centrifugal force. The speeder spring then pushes the pilot valve down. This action directs more high-pressure oil to the propeller hub. This oil pressure overcomes the counterweight springs and decreases the blade pitch, takes a smaller bite of air. A lower pitch reduces the load on the engine, allowing it to speed up and return to the desired on-speed RPM.
So it lightens the load to speed up.
Overspeed condition. Conversely, this occurs when the engine RPM increases above the pilot's set target, say. You push the nose down into a dive or encounter turbulence that momentarily unloads the prop. Now, the flyweights move outward due to the increased centrifugal force, overcoming the speeder spring tension and raising the pilot valve. This allows oil to flow from the propeller hub back to the engine sump. With the oil pressure released, the counterweights and springs are now free to do their job, forcing the blades to an increased pitch angle, a coarser pitch, bigger bite. This higher pitch increases the load on the engine, slowing it down until it returns to the target on-speed RPM.
Increases the load to slow down. It's a continuous dynamic dance.
It really is. It's constantly making tiny adjustments. It's worth noting, though, that at very low RPM settings, like during taxi or final approach, the propeller blades might actually hit their physical low-pitch stops. In this situation, the governor can't decrease the pitch any further, so the propeller essentially behaves like a fixed-pitch prop until the RPM comes back up into the governing range. The governor typically only has authority over a certain RPM range, maybe a couple hundred RPM wide.
That governor system is a truly remarkable piece of engineering, constantly adjusting for optimal performance. Now let's talk again about that crucial safety and operational feature, especially vital on multi-engine aircraft, feathering and unfeathering.
Right, minimizing drag from a failed engine.
With constant speed feathering propellers, the mechanism, as we touched on, often involves oil pressure moving the blades towards low pitch, while blade counterweights, and usually a powerful feathering spring, move them towards high pitch or the full feather position. The feathering process itself is typically initiated by the pilot. If an engine fails, the pilot pulls the propeller condition lever or prop control fully back into the feathered detent. This action mechanically causes the governor to dump all its oil pressure from the propeller hub.
Releases the force holding it in low pitch.
Exactly. With that controlling oil pressure removed, the powerful counterweights and the dedicated feathering spring then take over and drive the blades rapidly towards the feathered position. That's roughly 90 degrees pitch, edge onto the wind. This happens quite quickly, usually taking between 3 and 10 seconds, depending on the system.
A surprisingly fast transition.
There's also a clever safety feature often built in: automatic high-pitch stops or latches. These physically prevent the propeller from feathering at very low RPMs, typically below maybe 600 to 800 RPM. This is primarily important to avoid putting an excessive load on the engine starter motor during startup if the prop was accidentally left feathered. But this also means that if the governor oil pressure is lost in flight for any reason, like an engine oil leak or internal governor failure, the propeller will automatically feather itself because the oil pressure holding it out of feather is gone. This is a vital fail-safe feature, as it minimizes drag immediately and can protect the engine from further damage in the event of an oil system failure or even an engine seizure.
So loss of oil pressure equals feather. Good to know.
Now, to get that engine running again after it's been feathered, assuming the underlying problem is fixed or was shut down preventatively, you need to unfeather the propeller. You need to get it windmilling again so the engine can restart. There are a few common methods for this. One way is simply by restarting the engine using the starter motor, if possible. As the engine begins to spin, the governor starts pumping oil back into the propeller hub. This oil pressure overcomes the feathering spring and counterweights, reducing the blade pitch, which allows the propeller to start windmilling from the airflow, helping the engine to restart.
Using the engine itself to unfeather?
Another very common method, especially on larger aircraft, involves an accumulator system. This system essentially traps a charge of high-pressure oil, sometimes backed by compressed air or nitrogen, when the propeller is feathered. To unfeather, the pilot activates the system, usually holding a switch, which releases this stored pressure back into the propeller hub, forcing the blades out of feather and back towards a low pitch angle. This causes the propeller to start windmilling rapidly, allowing for a quick engine restart without relying solely on the starter.
A boost of pressure to get things moving.
Some aircraft might even have a dedicated electric unfeathering pump that forces oil into the prop hub specifically for this purpose. Regardless of the method, the pilot typically holds the unfeathering switch or control until the propeller is windmilling at a sufficient RPM for a successful engine restart.
It's all about getting those blades back into the wind. And the sophisticated control extends even further when we look at turboprop engines and their propeller control systems. Remember, unlike turbojets or turbofans that produce thrust directly from exhaust gases, turboprops generate almost all their thrust indirectly via the propeller. This means the engine's fuel control unit, FCU, and the propeller governor are even more intricately linked and coordinated.
They have to work together seamlessly.
Absolutely. The power lever in the cockpit essentially sends a signal for a specific amount of power or thrust. Then, the fuel control and propeller governor work together, communicating constantly to find the right combination of engine RPM, often denoted as NP for propeller RPM, fuel flow, and propeller blade angle to achieve that desired thrust efficiently.
It's a more integrated system.
Very much so. Turboprop propeller control systems typically have distinct operating ranges, often referred to as alpha and beta ranges. The alpha range is the normal range used for flight operations, from flight idle power up to maximum takeoff power. In this range, the propeller governor is in primary control of the blade angle, maintaining the selected N, while the fuel control adjusts fuel flow to meet the power demands set by the power lever.
So, like the constant speed operation we discussed.
Pretty much, yes. However, when the pilot pulls the power lever below the flight idle gate, they enter the beta range. This range is primarily used for ground handling and accessing reverse thrust. In the beta range, the propeller governor is effectively bypassed for blade angle control. Instead, the propeller blade angle is controlled directly by the position of the power lever. The further back the pilot pulls the lever into beta, the flatter or even more negative the blade angle becomes.
So the pilot is directly commanding pitch and beta.
Correct. This allows for precise control of thrust near zero or even into negative thrust, reverse, for braking after landing or backing up. The engine's fuel control might switch to managing NP in this range or follow a schedule based on power lever position. It's a different control philosophy for ground ops. Of course, to get the very high rotational speeds of the gas turbine engine, often tens of thousands of RPM, down to the optimal, much slower propeller RPM, usually kept below the speed of sound at the tips, turboprops require a robust reduction gear assembly. This is typically a multi-stage planetary gear system located between the engine's power turbine and the propeller shaft. This gearbox assembly often also incorporates propeller brake to stop the propeller from windmilling when the engine is shut down and feathered on the ground.
A critical piece of machinery, that
Yeah.
gearbox.
Absolutely. Modern turbopropeller assemblies are incredibly sophisticated, often utilizing dual FAD full authority digital engine control systems. These computers manage both the engine and the propeller together as a single integrated system, optimizing performance, efficiency, and safety across all operating regimes, including alpha, beta, starting, and transient conditions.
FADDC takes care of almost everything.
It manages a huge amount. A very popular example you'll find on many turboprops is the Pratt & Whitney PT6 engine, often paired with a heart cell propeller system. This typically uses a single-acting governor system, similar in principle to many piston constant speed props. Oil pressure is used to decrease pitch, while the feathering spring and blade counterweights increase pitch towards feather. In beta mode on these systems, moving the power lever aft directly controls oil pressure to set a specific blade angle for forward or reverse beta operation. There are complex valves, like a primary blade angle (PBA) control, and often a lock-pitch solenoid valve to ensure safe transitions and prevent inadvertent reversing in flight.
Lots of safety interlocks.
Always. And crucial overspeed protection is built in. There's usually a dedicated propeller overspeed governor separate from the main governor, with its own flyweights and springs, set to trigger at a slightly higher RPM, example, 104% NTP. If the main governor fails, this one dumps oil pressure to increase pitch and slow the prop down. Additionally, there's often an engine overspeed, NF or gas generator speed, governor within the fuel control unit itself. If the propeller or power turbine section exceeds a limit, say 106% RPM, this governor will automatically reduce fuel flow to the engine, limiting power and preventing a runaway condition.
Multiple layers of protection.
Definitely needed with the power these engines produce. Now, as an alternative to hydraulic control, some propellers, though less common now, were electrically controlled.
Instead of oil, they use electricity.
Exactly. These systems use a DC electric motor mounted in the propeller hub. This motor drives the blades through a high-ratio gearbox, often a planetary gear reduction system, to generate the high torque needed to change pitch against aerodynamic and centrifugal loads. Key components include the motor itself, a motor brake, usually spring-loaded on, solenoid released off so it fails safe by locking the pitch, the gearbox, the hub and blades, slip rings and brushes to get power to the rotating hub, a governor, which now sends electrical signals instead of controlling oil, and various switches in the cockpit.
How did the pilot control it?
The pilot typically has a switch with positions like off, increase RPM, decrease RPM, and automatic. In manual mode, increase, decrease RPM, it acts like a variable fixed pitch prop. The pilot directly controls the pitch motor. In automatic mode, the governor takes over, sensing RPM and sending signals to the motor to maintain the constant speed selected by the pilot. Some systems had a voltage booster to increase the electrical power available for quicker feathering or reversing operations.
What are the key differences from hydraulic systems?
Well, lubrication is one challenge. They need grease that can work in extreme cold, as there's no warm engine oil circulating. A major difference is failure modes. An electrical failure typically results in the motor brake engaging, locking the pitch wherever it was. This is different from hydraulic systems where loss of oil often leads to feathering. Also, electric systems generally don't have a limit on the number of feather-on-feather cycles, unlike some accumulator-based hydraulic systems.
Interesting trade-offs there.
Yeah.
That's a lot of intricate control just to make sure those blades are doing exactly what they need to do when they need to do it.
Yeah.
Now, once you have multiple engines, you introduce a whole new layer of complexity, particularly when it comes to passenger and crew comfort and also safety, things like propeller synchronization, phasing, and ice protection.
Right. Managing multiple spinning disks.
Anyone who's been on an older multi-engine propeller aircraft without proper propeller synchronization knows the problem. That annoying, headache-inducing thumping beat sound and the pervasive vibration that comes with it.
Whoop, 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 whoop.
Yeah, not pleasant. Not pleasant at all. It's not just an annoyance. Prolonged exposure can genuinely affect crew fatigue and passenger comfort. But more seriously, that constant vibration can also be detrimental to sensitive avionics and even cause long-term fatigue damage to the airframe itself. Historically, pilots would manually synchronize the propellers. They'd listen carefully to the beat frequency and adjust one engine's prop control slightly until the beat disappeared. Or they might use a visual technique called strobing, looking through the arc of the inboard propeller disc to watch the outboard one. When the silhouette of the outboard blade appeared stationary relative to the inboard disc, the props were synchronized.
Requires a good ear and good eyes.
Definitely. But thankfully, today we usually have automated synchronization systems. These use RPM sensors, often magnetic pickups, on each engine, feeding information to a control box. This box compares the signals and sends correction signals to one engine's propeller governor, usually designated the slave engine, to precisely match its RPM to the designated master engine. You might see a visual indicator in the cockpit called a synchronizing disc or synchroscope. If the pattern on the disc is stationary, the props are synchronized. If it rotates clockwise, the slave engine is faster, counterclockwise, it's slower. Pilots typically get the RPMs close manually using the tachometers, engage the synchronizer, and then the system fine-tunes and maintains perfect synchronization automatically. Modern F8E systems, as we mentioned, go even further, often automating both synchronization and the next step, synchrophasing, completely for the pilot.
Right, taking it beyond just matching speeds. Modern systems offer propeller synchrophasing. This takes comfort to the next level. It doesn't just match the speeds, RPMs, of the propellers, it also actively controls the phase relationship between the blades of the different propellers.
Phase relationship, what does that mean exactly?
Imagine the propellers are like clock hands spinning at the same rate, synchronized. Synchrophasing ensures that the hands, blades, on one clock engine are always at a specific optimal angular position relative to the hands on the other clock as they rotate. The purpose is to further reduce cabin noise and vibration. By carefully controlling this phase angle, the system can arrange the pressure pulses generated by the blades from different engines to interact in a way that minimizes the overall noise level reaching the fuselage. It's essentially trying to make the pressure waves interfere constructively or destructively in the most favorable way for quietness.
Like noise-canceling headphones, but using the propellers themselves.
That's a great analogy, exactly. It actively manages the timing of the bleed passages relative to the airframe and each other. Some systems allow manual adjustment where the pilot rotates a knob to find the smoothest, quietest phase by ear, while fully automatic systems handle this seamlessly based on sensor inputs.
That's incredibly sophisticated.
And the ultimate evolution in this area, found on the quietest modern turboprops like the Bombardier-8Q400, the Q stands for quiet, is the Active Noise and Vibration Suppression System, ANVS. This system actively supplements the FAX's synchronization and synchrophasing capabilities. It uses microphones mounted strategically inside and outside the fuselage to actually sense the noise and vibration levels in real time. Then, based on this input, a controller calculates and sends precisely tailored anti-phase noise-canceling signals to electronic transmitters, like speakers, also placed around the fuselage structure. These transmitters generate sound waves that are exactly out of phase with the offending propeller noise, effectively canceling much of it out before it reaches the passenger's ears. It works alongside passive acoustical insulation features to make the cabin remarkably quiet.
Wow. Actively fighting noise with anti-noise. Amazing. These comfort and safety features also extend to battling a very real and potentially dangerous adversary in flight, ice. Propeller ice protection systems are absolutely crucial, because even a small amount of ice accumulation on the propeller blades drastically alters their carefully designed airfoil shape. This causes a significant loss of thrust efficiency, creates severe aerodynamic imbalance leading to intense vibration, adds weight, and the shed ice can damage the aircraft. Not good.
Definitely not good. Ice is a major hazard.
There are two main approaches to dealing with prop ice. First, anti-icing systems. These are designed to prevent ice from forming in the first place. They typically work by dispersing a special freezing point depressant fluid, often isopropyl alcohol or sometimes glycol-based phosphate compounds, onto the blade surfaces during icing conditions. The fluid is pumped from a reservoir to a slinger ring mounted on the back of the propeller hub. Centrifugal force throws the fluid outwards through nozzles onto the blade roots or shanks. Rubber feed shoes or boots attached to the leading edges then help direct this fluid along the critical leading edge of the blade as it spins. The fluid mixes with incoming supercooled water droplets, preventing them from freezing and adhering to the blade.
Keeps the blades wet with antifreeze, basically.
Exactly. The advantages are obvious. No ice builds up if it's working correctly. But the disadvantages are that it adds weight. You have to carry the fluid. The duration is limited by the amount of fluid you have on board, and it can be largely ineffective if significant ice has already formed before you turn the system on. Also, the phosphate compounds, while less flammable than alcohol, are usually more expensive. So good for prevention, but limited endurance. Right. The second approach is de-icing systems. These are designed to remove ice after it has already formed on the blades. These systems almost always use electrical resistance, heating elements embedded within rubber boots, bonded to the leading edges of the blades, and often the spinner dome as well. Power is generated by the aircraft's electrical system and transferred to the rotating propeller assembly via slip rings and brushes located at the back of the hub. Heating the blades to melt the ice off? Correct. A crucial component in these systems is the sequencing timer. You don't want to heat all the blades or all parts of the blades continuously or simultaneously. That could cause uneven shedding, leading to imbalance, or worse, run back, where melted ice flows back past the heated area and refreezes into potentially more hazardous shapes. So the timer applies power intermittently and sequentially to different sections of the blades. For example, it might heat the outboard sections of all blades for 15-30 seconds, then turn off, then heat the inboard sections for 15-30 seconds, then turn off, completing a cycle perhaps every 90 seconds or 2 minutes. This allows a layer of ice to build, then the heat breaks the bond, and centrifugal force slings the ice off cleanly before significant runback can occur.
Time shedding for balance. Precisely. Pilots monitor these systems with an ammeter in the cockpit, which should show a current draw within a specified green arc when the heaters are active. You'll often see the ammeter needle flicker as the timer cycles between different heating elements. The main advantages of electric de-ice are that duration is limited only by electrical power availability, not fluid tanks. The main challenges. Well, the noise from chunks of ice slinging off the blades can be quite startling to passengers if they're not expecting it. Although, activating the system early, as soon as icing is encountered, can sometimes minimize the size of the chunk shed, effectively using it somewhat like an anti-icer.
Both systems need to work reliably. And of course, that means they require meticulous maintenance to remain effective when you really need them. For fluid anti-icing systems, maintenance involves things like inspecting the fluid reservoir for leaks, checking the quantity, periodically draining and flushing the system to prevent contamination. The pump, filter, and check valves need functional checks. Technicians might perform flow tests to ensure the correct fluid delivery rate is being achieved. At the slinger ring, the manual might specify, say, flow rates corresponding to 1 to 3.5 hours of operation from a 3-gallon tank, depending on the selected flow rate.
Gotta make sure the juice flows right.
Exactly. Electric de-icing systems require a different set of checks. During operation, pilots observe the ammeter for that steady green arc current draw, looking for the characteristic momentary flickers as the sequencing timer cycles through elements deviations suggest a problem with an element or connection. On the ground, technicians might perform tactile checks carefully to ensure the heating elements are actually getting warm during a ground test, verifying the heating sequence. The brush block assemblies, which transfer power to the slip rings, need careful inspection for cleanliness, carbon dust buildup, excessive or uneven wear on the brushes, proper spring tension, and correct alignment with the slip rings. There are often limit pins or wear indicator holes on the brushes, and electrically resistance checks are performed on the heating elements themselves using an ohmmeter. Technicians compare the measured ohmic values against the manufacturer's specifications. Readings that are too high, too low, or infinite indicate a fault within the element or its wiring. If the rubber overshoes boots are damaged, their replacement is a careful process involving special solvents, non-metallic scrapers to avoid damaging the blade, proper adhesion techniques, and applying a perimeter sealant to prevent moisture ingress. Safety precautions are vital when handling the chemicals involved.
It sounds like keeping these systems working is almost as complex as the propeller itself. All these complex systems, the incredible forces, the need for precise control, it all underscores that the lifespan of a propeller is heavily dependent on diligent maintenance, careful repair, and proper preservation. Due to the incredibly high stresses propellers endure, remember those tons of centrifugal force, maintenance is absolutely not a casual affair.
No, you can't just glance at it and say, looks okay.
Definitely not. Propeller inspection and maintenance involves routine visual and tactile inspections. You're not just looking, you're feeling for subtle irregularities, nicks, corrosion, looseness. On variable pitch propellers, technicians routinely check for play in different dimensions, grabbing a blade tip and checking for movement up and down, twisting along the pitch axis, pushing, pulling fore and aft relative to the plane of rotation. Some small amount of play might be normal in some axes, within limits specified by the manual. However, one critical check is in and out play, trying to physically push the blade into or pull it out of the hub along its long axis. Absolutely no perceptible play is allowed in this dimension. Any movement here indicates a serious internal problem with the blade retention system.
That's a critical safety check.
Blade assessment itself is about identifying common damage types and understanding their potential severity. Erosion from dust, sand, rain, especially near the fast-moving tip, is very common. Minor erosion on aluminum blades can often be carefully filed and sanded out by a certified technician, meticulously blending the repair to maintain the original airfoil contour. Impact damage from stones, tools, or unfortunately birds can range from minor nicks and scratches to severe gouges or dents. Nicks and gouges, particularly those with sharp bottoms or cracks radiating from them, are extremely critical because they act as stress concentration points. These tiny flaws can easily develop into fatigue cracks under the high cyclic loads, potentially leading to blade failure. Any sharp impressions must be carefully dressed out and blended smooth.
Removing that stress riser is paramount.
Corrosion is another major enemy, especially for metal propellers. You can get surface corrosion, pitting, small localized cavities, intergranular corrosion, attacking the grain boundaries within the metal, and even exfoliation, where the metal starts to separate in layers. This is why aggressive polishing is often discouraged, as it can remove protective finishes and hide underlying corrosion. Internal corrosion within the hub or blade root components is especially insidious because it's hidden from view, but can dramatically reduce the structural strength. Delamination, where the bonded layers separate, is a concern for wooden and composite blades. And lightning strikes, while rare, can cause significant damage, including arcing, burning, and even internal structural damage that might not be immediately obvious.
A lot to look for, and sometimes the most dangerous flaws are hidden. That's where NDT comes in.
NDT, non-destructive testing, going beyond what the eye can see.
Exactly. To find those hidden flaws without damaging the part, we rely on various NDT techniques. Dye penetrance. Good for detecting surface-breaking flaws like cracks. You apply a brightly colored or fluorescent liquid penetrant that seeps into any cracks. After cleaning the surface, a developer draws the penetrant back out, making the flaw visible under normal or black light. Surface preparation is absolutely critical for this to work reliably.
Makes invisible cracks visible.
Etching chromic acid. These are older methods, primarily for aluminum, involving chemical etching of the surface. Cracks show up as dark lines. They use hazardous chemicals, though, so less common now. Eddy current. This method uses an electromagnetic probe to induce electrical currents, eddy currents, in conductive materials. Flaws like cracks or corrosion disrupt these currents, which the instrument detects. It's excellent for finding surface and near-surface subsurface flaws and works on both ferrous steel and non-ferrous aluminum metals.
See just below the surface.
Ultrasound. A very versatile technique. It sends high-frequency sound waves into the material using a transducer. The waves bounce back from the back surface of the part or from internal defects like cracks, voids, or delaminations. By analyzing the timing and strength of these echoes, technicians can map out internal structures and find flaws. Works on metals, wood, and importantly, composite materials. Good for surface and deep subsurface defects.
Sound waves mapping the inside.
Magnetic particles, MPI. This method is used only for ferromagnetic materials, steel alloys that can be magnetized. The part is magnetized, and then fine iron particles, dry powder or suspended in liquid, are applied. If there's a crack or flaw near the surface, it disrupts the magnetic field, creating leakage fields that attract the iron particles, making the flaw visible. Excellent for surface and near subsurface defects in steel parts like hubs or blade shanks. Coin tap. This is a specific low-tech but effective ND2 method used primarily for composite or bonded honeycomb structures, including composite blades. You literally tap the surface lightly with a metal coin, like a quarter. A solid, consistent ring indicates good bonding. A dull, hollow, or dead thud suggests an area of delamination or debonding between the layers beneath the surface.
Simple but effective for composites. Okay, so after all that rigorous inspection using eyes, hands, and advanced NDT, you need to ensure the propeller is not just sound, but also spinning smoothly and true. This leads us to things like blade tracking and propeller balancing.
Keeping the vibration down.
Exactly. Blade tracking is the process of checking that the tips of all propeller blades are rotating in the exact same plane. If one blade tip follows a slightly different path than the others, maybe it's slightly bent or the hub isn't seated correctly, the propeller is said to be out of track. This condition causes vibration and uneven aerodynamic loads, which puts stress on the airframe, the engine, and the propeller itself, potentially leading to premature component failure. You check this typically by setting up a fixed reference point, like a wooden block with a pointer, very close to the propeller arc, carefully rotating one blade tip so it just touches the reference, and then rotating the propeller to bring the next blade tip to the same position. You measure the difference. The tolerance is usually very tight, often plus or minus a 1/116th of an inch. Causes can be a bent blade, a bent propeller mounting flange on the engine, or even improper or uneven torquing of the mounting bolts.
Small deviations matter a lot at high RPM.
And related to tracking is ensuring the blade angles themselves are correct and matched. Technicians use special propeller protractors. These can be large benchtop units for overhaul shops or smaller handheld or universal protractors for use on the aircraft to precisely measure the angle of each blade at a specific reference station. Adjustments can sometimes be made on controllable pitch props following specific procedures. One important note from the manuals. Never use a metal scribe to make temporary marks on blades during these checks, as even a tiny scratch can become a stress riser. Use a grease pencil or marker instead.
Attention to detail is everything.
Now, propeller vibration diagnosis can be tricky. It's often difficult for pilots or mechanics to distinguish between vibration originating from the engine versus vibration from the propeller assembly. Generally, propeller-related vibration tends to be felt throughout the entire RPM range, whereas engine vibration might be more pronounced at certain specific RPMs. Sometimes, observing the propeller hub while it's rotating from a safe distance can help if the hub itself appears to be orbiting or moving eccentrically. That strongly suggests a propeller imbalance or tracking issue. Common causes are physical imbalance, uneven weight distribution, blades out of track, or mismatched blade angles.
Finding the source is key.
Which brings us finally to propeller balancing. This is critical for smooth operation and longevity. There are two main types: static balancing. This is the most basic form, ensuring the propeller center of gravity, CG, aligns perfectly with its axis of rotation when it's not spinning. It's typically done during manufacture or overhaul on a specialized, nearly frictionless, knife-edged test stand in a draft-free room. Static balancing. You place the prop horizontally on the stand. If it rotates, it's unbalanced. For a two-bladed prop, you check it both horizontally and vertically. For 3 or more blades, each blade is positioned downwards and turn. Any tendency to rotate indicates an imbalance, which is corrected by carefully adding or sometimes removing small, permanent balance weights at manufacturer-specified locations, usually on the hub or blade clamps, until it stays perfectly still in any position.
Balancing it at rest.
Dynamic balancing. This is a much more advanced technique performed on the aircraft with the engine running, usually at cruise RPM. It uses sophisticated electronic equipment, typically one or more vibration sensors, accelerometers, temporarily attached to the engine casing, and a phototachometer sensor that provides an RPM signal and a phase reference, usually using a piece of reflective tape on the spinner backplate. These sensors feed data into an analyzer unit. The analyzer measures the amplitude, severity, and phase angle location of the vibration. Based on this data, the analyzer calculates the exact amount of weight needed and precisely where it should be added to the propeller spinner assembly to counteract the imbalance.
Balancing it while it's spinning.
Exactly. Dynamic balancing specifically reduces vibration caused by the mass imbalance of the entire externally rotating assembly, propeller, spinner, mounting hardware. It provides a much smoother ride, significantly improving cabin comfort, reducing fatigue for passengers and crew, and minimizing long-term vibration damage to the airframe, avionics, instruments, and engine components. The procedure involves inspecting and cleaning the prop, attaching the sensors carefully, avoiding hot or rotating parts, performing an initial engine run-up to stabilize temperatures and RPM, collecting the vibration data, and letting the analyzer compute the correction. Small temporary weights are added at specific locations, often designated screw holes on the starter ring gear or spinner bulkhead. Then another run is performed to verify the improvement. It's often an iterative process, making small adjustments until the vibration level is reduced to a very low target, typically 0.2 inches per second IPS or less.
A very precise fine-tuning process, and crucial for keeping everything running smoothly and lasting longer. To keep all these moving parts, especially inside controllable pitch hubs, operating smoothly, propeller lubrication is absolutely crucial. This is especially important where you have dissimilar metals in contact, as the grease provides not just lubrication but also a barrier against galvanic corrosion. Maintenance manuals specify lubrication intervals, typically every 100 flight hours or 12 calendar months, whichever comes first. These intervals are often reduced for aircraft operating in harsh conditions like dusty environments or near salt water. It's also noted that new or recently overhauled propellers might require lubrication sooner than the normal interval, perhaps after the first 25 hours. This is because the initial operation can cause the grease to redistribute due to centrifugal loads, potentially creating voids where moisture could collect, leading to imbalance or internal corrosion.
So greasing isn't just about reducing friction.
No, it's very much about corrosion protection, too. The procedure usually involves carefully pumping the specified type of grease into fittings on the hub using a grease gun until clean grease is seen emerging from relief ports or around blade seals. This purges any old grease and contaminants. The amount is usually specified, often around 1 fluid ounce per blade, which might equate to about 6 pumps from a standard grease gun. Overgreasing should be avoided as it can damage seals.
Right amount, right place, right time.
For controllable pitch propellers that rely on a dry nitrogen or air charge in an accumulator or dome to assist with pitch changes, often towards high pitch feather, maintaining the correct propeller air dome charging is essential for proper operation. Nitrogen is generally preferred over air because it's inert and dry. Technicians use specialized charging equipment and refer to temperature pressure charts found in the maintenance manual. These charts are critical because the pressure required varies significantly with ambient temperature. You need the correct charge pressure for the current temperature to ensure the propeller can function correctly through its full pitch range, including feathering if applicable.
Temperature matters for pressure.
Absolutely. And another critical safety check, often done concurrently with propeller maintenance or balancing, is the tachometer check. The tachometer is the primary instrument the pilot uses to set and monitor engine propeller RPM. An inaccurate tachometer is dangerous. It could lead a pilot to inadvertently operate the engine and propeller outside their safe RPM limits, either overspeeding, which causes excessive stress and vibration, or underspeeding, which might prevent developing full power. Regulations typically require tachometers to be checked for accuracy, often within plus or minus 10 RPM or a small percentage, at 100-hour or annual inspections. This check is usually done using a calibrated handheld electronic tachometer or by comparing the cockpit touch reading to the precise reading from a dynamic balancer's photo touch during balancing.
Gotta trust your gauges.
You really do. Simple cleaning propellers is also part of routine maintenance. Oil and grease streaks are common, especially around the hub seals, and need to be cleaned off partly for appearance, but mainly so that any new leaks can be easily spotted. Propellers should be cleaned using approved solvents on a rag to remove grease, followed perhaps by mild soap and water. It's crucial to avoid using harsh abrasive brushes, steel wool, or high-pressure power washers, as these can damage the protective paint or plating, erode the blade material itself, or force water-past seals into the hub mechanism. In saltwater environments, flushing the propeller assembly with fresh water after flight is highly recommended to prevent corrosion.
Gentle cleaning is key.
When it comes to propeller repairs, it's vital to understand that only very minor repairs are permitted to be performed in the field by appropriately certified technicians. Things like dressing out small nicks or corrosion pits. Major repairs, like straightening bent blades, welding, major composite repairs, or complete propeller overhauls, due to the incredibly high stresses involved and the catastrophic consequences of an in-flight failure, must be performed by specialized, manufacturer-approved propeller repair stations or the manufacturer themselves. They have the specific tooling, data, expertise, and authority to do this work safely. Minor repairs, like dressing out nicks and gouges, involve carefully filing and then sanding the damaged area to remove the stress riser. The key is to create a smooth, shallow depression with well-feathered edges, blending it back into the original contour. Manuals give specific limits on the depth of damage that can be repaired, and the shape of the repair often requiring the length of the blended out area to be at least 10 times the depth for leading trailing edges, and maybe 20 times the depth for repairs on the blade face or back. After dressing out the damage, the area must be inspected, often with dye penetrant, to ensure the flaw has been completely removed. And then the protective finish, paint, or chemical treatment must be carefully reapplied.
Very precise work, even for minor repairs.
Absolutely. A propeller overhaul is a much more comprehensive process, performed at specified time intervals, TBO time between overhaul or on condition. It involves completely disassembling the propeller down to its individual components. Everything is thoroughly cleaned using various methods. A detailed preliminary inspection identifies any obvious damage. Critically, all threaded fasteners, bolts, nuts, screws, are typically discarded and replaced with new ones during overhaul. Then, every part undergoes meticulous dimensional inspection, measuring critical tolerances against the original manufacturer's specifications using precision instruments. Metal parts might be reanodized or cadmium plated to restore protective coatings. Hub components undergo rigorous NDT inspections, like LPI, eddy current, or MPI, to check for hidden cracks, especially in high-stress areas. Blades themselves are overhauled, precisely measured for width, thickness, twist, and face alignment. Minor damage is repaired. They might be surface ground to remove corrosion, repitched if necessary, or even carefully straightened if bent within strict limit. Finally, the propeller is painstakingly reassembled using new seals and hardware, lubricated, and undergoes final checks for high and low pitch blade angles, static balance, proper safety wiring of all fasteners, and a final inspection before being certified as airworthy and returned to service. It's an incredibly thorough and regulated process.
Restoring it to, like, new condition, basically.
That's the goal. There's also troubleshooting propellers, diagnosing common issues like hunting or surging, RPM fluctuating in constant speed mode, often pointing to governor issues, fuel control problems, or synchrophaser interference, or perhaps a failure to feather, which could be low accumulator air charge, incorrect control rigging, internal friction, or faulty valves. Maintenance manuals provide detailed troubleshooting charts for these scenarios, and the propeller governor itself requires inspection and occasional adjustment. Routine visual checks look for oil leaks, security of mounting, correct rigging, and full travel of the control linkage. Operational checks are crucial after any propeller or governor replacement. This includes a static RPM test, running the engine at full throttle with the aircraft stationary and the propeller control set to high RPM. The maximum achievable RPM is checked against the aircraft's specifications. If the static RPM is slightly off, minor adjustments can often be made to the governor's maximum RPM stop screw. For example, the manual might say 1 full turn changes static RPM by 25 RPM. It's important to distinguish if low static RPM is due to the propeller blades reaching their low pitch stops, an airframe propeller limitation, versus needing a governor adjustment.
So much to keep track of. And finally, after all this operation and maintenance, protecting these vital components during periods of inactivity is just as important. This is where propeller storage and preservation comes into play, especially crucial if the aircraft isn't flown regularly or is stored in harsh environments.
Can't just let them sit out in the elements indefinitely.
Exactly. Manuals often define categories for storage. Flyable storage, for aircraft flown at least monthly, usually just requires keeping things clean and maybe more frequent lubrication, for example, every 6 months, if in very humid or corrosive environments. temporary storage, for aircraft inactive for up to maybe 90 days. Often benefits from engine preservation procedures, and again, maybe 6 months greasing intervals. Indefinite storage for long-term non-use. This requires more extensive preservation, like filling the hub internally with preservative oil after draining engine oil and relieving any accumulator pressure.
Different levels of protection for different downtime.
General measures for any storage include keeping the propeller clean. Bird droppings, for instance, are surprisingly corrosive. Applying a thin film of water-displacing preservative compound, like AMEL C46173 Grade 2, to external metal surfaces is recommended, but importantly, avoid applying these petroleum-based compounds to rubber components like de-icing boots, as they can cause deterioration. Wooden propellers, as we mentioned, have specific needs. They should always be stored horizontally if removed from the aircraft to maintain balanced moisture content and prevent warping. Ideally, they should be removed from aircraft left outside in heavy snow or extreme heat and sunlight for extended periods and stored indoors, preferably in a climate-controlled environment. Metal adapters or hubs on wooden props should also be preserved.
Wood needs extra care.
For long-term storage of metal propellers, techniques can include corrosion-inhibiting plating on internal parts, filling internal passages with preservative coatings or oils, like AMEL C16173 Grade 2 for external metal, AMEL C6529 Type 2 or 3 for internal hub governor accumulator components, and physically covering the propeller. This covering should be with non-hygroscopic material, doesn't attract moisture, like special coated paper, plastic sheeting, vinyl covers, or durable bags. For maximum protection, propellers can be sealed in containers with dry nitrogen gas purged in, along with desiccant bags to absorb any residual moisture.
Similar procedures apply to storing governors and accumulators separately. Flush and fill passages with preservative oil, install protective covers on openings, and crucially, ensure any pressure is completely relieved from accumulators before storage.
Locking them down safely for the long haul.
And finally, depreservation return to service after storage is just as important. It involves carefully draining any preservative fluids, thoroughly inspecting all components, especially rubber parts like seals and O-rings, which may need replacement, reinstalling the propeller correctly, paying attention to O-rings, clock angle indexing if applicable, proper torquing and safetying, removing protective films, re-lubricating as required, recharging air domes, reconnecting control systems, and performing thorough post-installation ground tests. These tests would include checking static RPM, cycling a propeller pitch multiple times, checking feathering and unfeathering operation, and testing the de-icing system if installed, all before the aircraft is returned to flight status.
Wow. Okay. What a journey. From what seems like just a simple spinning blade, we've really unpacked a genuine marvel of engineering, physics, and just incredibly meticulous maintenance. It's truly a testament to the hidden complexity often lurking in seemingly straightforward devices.
It really is quite amazing when you break it down.
So what does this all mean? Well, I think it means every time you hear that distinct hum or buzz of a propeller, whether it's on a small single-engine Cessna, aerobatic stunt plane, or a massive multi-engine turboprop, you're not just hearing an engine doing its thing. You're hearing this whole symphony of powerful forces being constantly balanced, advanced materials enduring incredible stress, and precise control systems, making adjustments potentially thousands of times per minute, all working together in perfect harmony to push that aircraft forward through the air.
Absolutely. A symphony is a good word for it. And we really hope this deep dive has given you, our listener, a much deeper, maybe even a profound appreciation for propellers. Hopefully, we've transformed some of what you thought you knew into genuine aha moments about this truly fundamental component of aviation. And the technology hasn't stood still. From the Wright brothers' initial brilliant insights about propellers as rotating airfoils, grappling with those basic forces, all the way to today's advanced, sculpted composite blades, fully automated FAD engine and propeller management systems, and even those active noise suppression technologies. Propeller technology continues to evolve, constantly pushing the boundaries of efficiency, performance, and quietness in flight.
Still innovating after more than a century.
Constantly. So here's a final thought to leave you with. Consider next time you see or hear a propeller aircraft, just how that seemingly simple device is silently battling tons of centrifugal force, how it's precisely adjusting its angle of attack maybe thousands of times per minute to stay efficient, and on some aircraft, even actively canceling out its own noise, all just to push an aircraft forward. What other everyday technologies that we take for granted hold such complex, hidden worlds of engineering and physics just waiting inside them, waiting to be explored? Keep asking questions, keep digging,